Well, hello, everyone. Thank you for joining us this evening. This is the fourth talk in the series of talks that are being sponsored this year by Climate Reality Project and Silicon Valley chapter, and the Sierra Club Loma Prieta chapter, also here on the peninsula. So my great pleasure this evening to introduce Brent Constanz, who is the founder, chief executive officer, and chief scientist of Blue Planet Systems. Brent received his Ph.D. in earth sciences at the University of California in Santa Cruz, and then as a Fulbright Scholar, studied at the Weizmann Institute in the field of bio-mineralization, I can hardly say it. That's the process by which living organisms produce materials such as shells, bones, and teeth. So after that stay in Israel, Dr. Constantz has founded and led as CEO 3 medical device companies applying mineralization technologies for orthopedic bone cements. He then founded Calera Corporation, which is a carbon and cement related corporation, as well as Blue Planet Systems, where he is currently CEO and chief scientist. This addresses global climate concerns by permanently sequestering gigaton quantities of carbon dioxide in the form of carbonate minerals, think concrete. Dr. Constantz has over 100 US patents with another 100 pending. And today he's going to tell us about storing 1 billion tons of carbon dioxide in the built environment. So Dr. Constantz, I'll hand it over to you.
Great, thanks, Scott. And it's nice to be here. My computer won't advance in full screen mode for some reason. So let me start sharing again, and we'll kick it off. The way I'd like to start off is talking about carbon in general, and really back up to just sort of the fundamentals of carbon. On Earth, if I were to ask most people, where do you think all the carbon is? Most of us would say in the atmosphere is carbon dioxide. But if you actually look and see where all the carbon is, what you find out is most of it is not as carbon dioxide. In fact, very little of it is in the form of carbon dioxide. And the really predominant forms of carbon on Earth are in the form of bicarbonates or carbonates. For example, in this cartoon, you can see how 1 billion tons or 1 gigaton is equal to about 6 million blue whales, just to give you a feeling for what a billion tons or a gigaton is. And so if we go to the atmosphere, which is, an envelope of gas around Earth, which is, less than 100,000 feet thick, there's about 800 billion tons or 800 gigatons of carbon in Earth's atmosphere. And this is what accounts for the 410 ppm you hear about in the atmosphere. But if you go to the whole biosphere, both the terrestrial biosphere, including soil and all the plankton in the ocean, all the biomass, it's about 2,400 billion tons, 2,400 gigatons. But if then you go to the hydrosphere, all the oceans, rivers, lakes, oceans, ice caps, there's almost 40,000 gigatons of carbon in the oceans, mostly in the form of bicarbonate, whereas in the biosphere, it's mostly in the form of more interesting biologic molecules. But look, there's over 10 times more carbon in the oceans than the whole biosphere, and it's in the form of essentially Perrier. and that's where it is. But then if you go from the biosphere to the lithosphere, and look at the crust of the Earth, about 10% of Earth's crust is carbonate rocks or limestone. And there's approximately 100 million billion tons of carbon in the lithosphere in the form mainly of limestone. And I'm talking about the White Cliffs of Dover, the calcareous oozes on the ocean floor, the Great Barrier Reef, the Austin Chalk. That's where, for all intents and purposes on a grand scale, all Earth's carbon is already in limestone. And more importantly, and this will be a sort of fundamental aspect that I'll run through, is very little of it is as CO2, and most of it is CO3, either carbonate or bicarbonate. And here on the right is just a phylogenetic tree of calcifying organisms. And this is just to point out that almost all the limestone on Earth is the skeletal remain of an ancient marine organism, like a coral or a coccolith or a clam or calcified algae. And that's still a process that is very robust. For example, we're all familiar with lobsters and, who have an exoskeleton. You probably know that a crab or a lobster shed their exoskeleton in order to grow. They don't have internal bones like us. They have a shell on the outside. And when they need to grow, they shed the whole skeleton. And then they grow a little, and then they have to recalcify a new skeleton. They do that in hours because they're subject to predation. And if they shed their skeleton and go very long without remineralizing the skeleton, they're out there like entrees on the sand in the ocean. So the reason that's significant is they use some really interesting chemistry to do that. And it's really a phenomenal feat, and it's not very well understood by anybody. And that's similar to the kind of science that we use. So having said that, at Blue Planet, we don't work with carbon dioxide at all. We are able to capture very large amounts of carbon dioxide out of anything from the atmosphere to a pure stream of CO2. But that's the only time we come into contact with CO2. We say we only touch it once. And it's in that millisecond that we absorb CO2 gas into an aqueous solution to form carbonate, which is a spontaneous downhill reaction. So for example, in this slide on the left shows Blue Planet collecting CO2 from some, let's pretend these are natural gas-fired power plants or cement plant, from a dilute stream, that might be 5 to 30% CO2, and converting it to carbonate and bicarbonate. It is essentially the same concentration, and then forming calcium carbonate and turning that into limestone. The entire rest of the field working in carbon management is doing what's on the right, which is working with purified CO2, either bringing in purified CO2 or capturing it and concentrating it, which is a energy intensive process, even trying to purify it, putting it in pipelines that can handle high pressure with compression stations, building pipelines to transport it. And the common idea, the current paradigm is that we're going to build huge projects based on subsidies from the government to inject it underground and monitor it for some undefined period of time. And so essentially treat it like garbage and pay people to remove it. And so there's really a fundamental difference. But in the end, the limestone we make, which ends up in the built environment, is the desired endpoint for what's called CCS, or carbon capture and sequestration. Now, this whole field exists primarily for to support the oil industry, for enhanced oil recovery, to inject liquefied, purified CO2 into depleted oil fields and push more oil out of the field. But you can't, come into contact with this field today without seeing, something, either state governments or the federal government or voluntary carbon markets, from companies like Microsoft, providing a financial incentive to follow this paradigm, with a concept that there's a calculation that there's enough pore space in the crust of the earth to securely store that much CO2. The methodology used to calculate that pore space is exactly the same methodology used to calculate whether there's an oil field trapped in a certain place. And it's an incredible disconnect, but the folks modeling it don't realize that most of the oil wells that they model don't hit oil. It's sort of a crapshoot. The truth of the field is most of the good places to do CCS were taken 20 years ago. And what's left, there's thousands of sites, but maybe 1 out of 100 is even worth exploring. But the main barrier to it is it's dependent entirely on subsidies. And it's not like subsidizing a solar farm, because when the subsidies go away, you still got a solar farm. Here, when the subsidies go away, you're done. You no longer have that's from personal experience. About 15 years ago, we were building a carbon plant down in the Latrobe Valley north of Melbourne. And the prime minister at that time had passed some really great subsidies for capturing CO2. And then, in fact, we got a $120 million grant from the Australian federal government and the Victorian state government. And anyway, a new prime minister, Rudd, came in, and within a very short period of time, between the time he came into office, he eliminated all the carbon subsidies. And all the money and all this, everything came to a halt, and nobody pursued it anymore. So it's very risky building a business, assuming that the government's going to pay you to clean up. And it's also really only prevalent in 5-10% of the world. Indonesia, India, they're never going to do CCS. I mean, they're never going to have the $100 a ton or whatever it is necessary to develop these fields. So that's sort of the harsh contrast between, I guess we're the Uncola. We put together quite a team. I'm not going to introduce everybody. I'll point out our most recent addition, David Gottfried, founded what's called the U.S. Green Building Council and developed what's called the LEED scoring system for green buildings. It's the most used building rating system in the world. And he also founded the World Green Building Council. And he just showed up one day and said, look, you guys are it. I want to dedicate my life to this, and this is what I want to do. So I think all you are already familiar with some of the goals for net zero emissions. So I'm not going to reiterate other than to say, there's obviously a lot of, the light blue is the industrial sector. The dark blue is electricity. the orange is transportation, and the super light blue is buildings. But there are companies all over the world and governments that have made these targets for lowering their CO2 output. And so there's a major push all over to find solutions, and there really aren't many solutions. So one aspect of what we're doing is we're not purifying CO2. So we can take in CO2 from any source. It could be very dilute, or it could be quite concentrated. For example, our largest investor and one of our big partners is a company called Sulzer, which is a Swiss company. It's sort of the Rolls-Royce of gas liquid contactors. And we've worked with everything from just the air, which is 0.04% CO2, to pure CO2. And that's one aspect that we're sort of having to educate the market about, because historically people managing CO2 have only worked with purified CO2 gas that can be liquefied. And we don't do that. We're able to address all of these CO2 sources in different ways and take it in. Now, you might ask, how come we were working on the rock? And so you all know that concrete, which is the most used building material in the world, you can't avoid stepping on it every day, is a mixture of sand, gravel, which we call aggregate, and cement and water. And most of the carbon footprint of concrete is coming from the cement. In this case, what we're looking at is this cement is about 96% of the entire carbon footprint of the concrete. So of course, do what I did. I formed Calera and built a power plant over at the Moss Landing power plant just to capture CO2 and make a replacement for Portland cement. So it was not only displacing the Portland cement, but it also was capturing CO2 with the material. So you're both eliminating the Portland cement footprint, but also sequestering CO2 in the cement. But what I learned by about 2011 was that even if you replaced all the cement and all the concrete in the world with a carbon neutral cement or a carbon negative cement, you'd still be a few billion tons. So humans put out whatever 30 or 40 billion tons of CO2. Even if we completely eradicated cement, we'd be addressing less than 10% of the problem. And, in founding Blue Planet, it wasn't to make a low carbon green cement, to compete with any other low carbon cement. We have such power. It was really identifying concrete as the most used building material. And the fact that the majority of the mass of concrete is not the cement, it's actually the sand and gravel. It's like 3/4 of the mass of the cement. And since our goal was to capture as much CO2 as we could and find a sustainable, meaning both technologically and economically sustainable reservoir to put all this CO2, to put tens of gigatons of CO2 away, we haven't found any other reservoir that's anywhere close to what you can do year in and year out, funded by the same dollars that are already funding the concrete, with all the same infrastructure already in place. Anything that comes close to concrete is where we're going to put the CO2. And it's striking with all these government subsidies coming out for what's called direct air capture. We literally have had dozens of direct air capture companies come to us to see if we would do something with their CO2, which they've spent a lot of energy on trying to purify and liquefy and put in pipelines. And there just really aren't a lot of options. And even if you wanted to do conventional geologic sequestration, the actual, I mean, there are whole countries like Singapore that just don't have places to do that. So it's not even an option. But the point is, we can take a yard of concrete and put a lot of sand and gravel in there. And I just to kind of go back to a little bit of chemistry, limestone is primarily calcium carbonate. And calcium carbonate has a molecular weight of 100 grams per mole. And there's one CO2 in every calcium carbonate transformed to CO3. So 44% of the mass of a yard, a ton of concrete is CO2. So if I have a ton of limestone that we've synthesized, then I have 440 kilograms of CO2 that's now permanently captured and mineralized in the crystalline state for millions of years, essentially for eternity. And by doing it in the sand and aggregate that goes into the concrete, it's also the most used building material in the world. It's ubiquitous. It's used in poor countries and rich countries, small villages, big cities. It even has a huge circular economy aspect to it, which I'll touch on, meaning when we're done with concrete, most concrete lasts 40 to 70 years. Instead of using it as landfill, it can actually be recycled and not transported, not transporting new limestone in. So anyway, if you look around the cement industry, they're under a lot of pressure, but they really haven't come up with any solution that's going to do much more than sort of drag them along into some forced promises that really aren't going to change things all that much. And there's a lot of policies being worked on today. The most interesting are not voluntary. They're related to using government procurement dollars to encourage low carbon or embodied carbon concrete. For example, here in California, we have a legislation that's being developed right now. It's passed the committee, a couple of committees. It says the state government is going to prepay up to 10 years in advance for low carbon concrete in their projects. And the state of California is one of the largest concrete consumers in the world, to encourage the development of low carbon concrete. But ultimately, the point is, instead of relying on government subsidies, which they're never going to be enough of and won't be available in most of the world where they're needed, and will never have any effect on climate change, instead, just use the government procurement dollars that are already available in rich countries and poor countries, but spend it on rock that's made from CO2 instead of opening up new open pit mines, transporting it long distance. I think I mentioned there's a new rating system that's come out. It's based on the Energy Star for energy efficiency, but this is on embodied carbon. It's called Carbon Star. And it can be used as a procurement criteria that, you know, to meet a certain bid or government contract, it has to have a certain carbon value, which could be carbon positive, carbon negative, carbon neutral, and it's defined. So there's a lot of aggregate mined every year, year in, year out, globally, a lot in the United States, even more in China, anywhere you're doing concrete. So when we look at how much CO2 could we really reasonably expect to get into the market this way? So if we assume that humans are putting out 34 gigatons of CO2 a year, you know, and y'all know there's a number of different numbers there, but that's a good conservative one. We're saying by 2030, Blue Planet will probably have 200 megatons or 0.2 gigatons out that we're capturing every year. And by 2050, our models show about 500 megatons or 5 gigatons. And that translates to, about 12 gigatons of rock going into a market of 55 gigatons. And so the key point here is that there's already money paying for that 55 gigatons, as well as there are systems to transport it, pay for it, building codes. There's no subsidy needed. So when people get into this field and start looking at all the things people are trying to do to concrete, there was one analyst report put together that was very well done. And he said some people are trying to make concrete more carbon friendly, if you will, by replacing the aggregates, which is where Blue Planet lies. Some people are trying to work on the cement like I used to do. And there's a number of companies working on that area. Some are making supplements to cement. Some are just buying CO2 that would be used for making Coca-Cola and trying to inject it into concrete without losing most of it into the atmosphere while they do it. And to make sense of that, the researcher used the carbon star rating system, which gives you the embodied carbon in a cubic meter of concrete. So kilograms of CO2 per cubic meter. And if you look at an ordinary concrete mix design, and again, that's mainly from the Portland cement, it's about 380 kilograms per cubic meter is the embodied carbon, or if you will, the carbon footprint, the production cost of the concrete. So if you take this technique where you perfume the molten concrete with purified, liquefied, pressurized CO2, it has a small effect. And all of these incremental approaches have some small effect. But as soon as you start working on the aggregate, which is most of it, that's where you get these really major reductions in CO2 if you're really trying to capture and sequester a lot of CO2. Also, owners and specifiers and governments want to have the most carbon negative material they can. Like if you're LinkedIn and you're owned by Microsoft, and Microsoft wants you to have a zero carbon new campus in Sunnyvale, there's no way to do that except really to go for the concrete. And if you have really negative carbon concrete, then not only can you offset all the carbon that the regular concrete would have caused, you can also be left with a carbon bank account from day one and offset your operational carbon in the future years. Because, embodied carbon all comes in on day one when you build the structure. Whereas, say you're a data center, you're looking at the carbon footprint spread over 20, 30, 40 years. But, if you look at the discounted value of carbon, there's a lot to be said for getting a lot of that carbon removed and sequestered on day one. So we need a lot of different things to put together. We need carbon dioxide, we need calcium, we've put the technology together, we understand the building inputs, and ultimately the built environment. So for example, in the area of feedstock, at our plant up in Pittsburgh, California, we get our calcium from old demolished concrete or returned concrete. And instead of mining new rock in British Columbia and bringing it down to San Francisco in barges like we do now, there's actually plenty of aggregate that's just being demolished and used as landfill that can be reused and provide the calcium and other aspects that you need. And, when you talk about the circular economy, you're talking about plastic bottles and aluminum cans, but what you're really talking about from a mass point of view is concrete. Literally, the majority of what we call the circular economy is really concrete being moved around. So we're working with CO2 emitters and concrete off-takers all around the world in a number of different verticals. Even this new area called direct air capture, where the government is providing a lot of money for people to provide methods to pull CO2 right out of the atmosphere. I'll make some other comments on that in a second, though. So this is just another kind of educational slide, if you will. We look on the left here, this blue circle is a representation of the volume of 1 ton of CO2 when carbon is in different forms. And when you calculate these as spheres, if you take a cubic meter of mother of pearl, which is pure calcium carbonate almost, it occupies about 1 cubic meter. As a liquid CO2, rather than a solid calcium carbonate, it occupies about 1.1 cubic meters. As a calcium carbonate, like one of our aggregates, like the type we used in the airport, that's lighter weight and it's porous, it's 1.6 cubic meters. In the bicarbonate solution, which is what we form the instant we the CO2 and the flue gas equilibrates with our capture solution, it's about 11 cubic meters. But unlike the liquefied CO2, it's not under any pressure or temperature control. It's just bicarbonate solution. If you have purified CO2 just in gas form, it occupies about 25 cubic meters. Or if it's the 5% CO2 flue gas that we're capturing at the Los Medanos Energy Center that Calpine owns in Pittsburgh today, that powers a lot of the city and county of San Francisco, it's about 80 cubic meters. And if you do what the government subsidies are focused on, 1 ton of CO2 would take 1.25 million cubic meters to treat to get 1 ton out of it. So that's approximately 1 Houston Astrodome to get 1 ton of CO2. So this is a real hot subject with a lot of the governments is we're going to go to the atmosphere and process it and take all the CO2 out. On the right here, with that knowledge behind us, we're kind of looking at the status quo, where the government has already picked a winner, which is CCS. So if you look at carbon capture and sequestration, you're usually not working with purified CO2 like an ethanol plant. You're usually talking about a coal plant, a natural gas plant, a cement plant, a steel mill, a refinery, which are putting out carbon streams that are dilute and mostly nitrogen or a lot of nitrogen, basically air. And purifying it with a lot of energy and compressing it with a lot of energy, putting it in pipelines, which require a lot of permitting and decades to build, and permitting and renting pore space and subsurface geologic reservoirs, or if you're an oil company, using it for enhanced oil recovery, Occidental Petroleum's teamed up with one of the direct air capture companies to get the low carbon fuel standard from the state of California to pump more oil out of their well by pushing CO2 from direct air capture into the ground. What we do at BP is just different. We, within the first instant, we, through the Sulzer absorber, we capture the CO2 and transform it through equilibration right into the solution. We put in a water pipeline and pump it to wherever the Blue Planet process is, which can be quite a distance. And it's essentially a water, and pump it back to absorb more CO2 after we've taken the chemicals out that we extract from our raw materials. So if you compare number 3 here, which is the status quo versus what Blue Planet's doing, we use about 1/40th the amount of energy to move the same amount of carbon the same distance. And the capital cost savings is even more extreme. And we really think that, as we've demonstrated this new method of large-scale carbon management, a lot of this talk you hear about CO2 hubs and pipelines for purified CO2, that whole conversation, we think, is going to change. Because it's hard to imagine why you would ever purify, compress, liquefy, transport CO2 to treat as garbage, when for a fraction of the cost, fraction of the energy, you can make a viable product out of it. Anyway, we have a bunch of patents all over the place, but the products that we produce are synthetic limestone, both in the form of a gravel and a sand, which we can make the principal component of the concrete. Here in San Francisco, we don't do this everywhere. We use demolished and returned concrete as our calcium source. And it's brought into us at no charge by the local, concrete recyclers. We extract calcium oxide out of it. And what's left over is a cleaned up aggregate that can go into the circular economy. So this is where, instead of bringing fresh virgin rock from British Columbia or the Sierra foothills, we can upcycle the old concrete that would have been landfilled or used as road base into a good structural sand. And some people might already know, but there's a global shortage of sand. Even in the Middle East, it's hard to come by. So we're serving all applications. This is where the rubber hits the road. So here's San Francisco Airport. And in the boarding areas, we used, it's called lightweight aggregate. It's one of the types of aggregate we can make. But what I want to draw attention to is, to even bid on a job at SFO, it has to meet a certain carbon star standard. So here they're specifying a certain carbon level, 200 pounds per cubic yard. So a regular yard of concrete would be 600 pounds per cubic yard. This is 1/3 of that, which you can almost achieve with just standard methods without Blue Planet. But they also have what's called a reach goal, which is 0. So the concrete is literally carbon neutral, and a regenerative goal, which is negative 200 pounds. So you can make your whole structure carbon negative and start off with a carbon bank account on day one. What we're doing now is, if you were to come up to Pittsburgh, this is our plant. Behind it is the Los Medanos Energy Center, which can put out up to 2 million tons of CO2 a year, depending on how much it's running. We've got pipelines running across the street over to our land, which is on the waterfront, where we can bring in, 70,000 ton Panamax vessels. We've been operating this one plant for about 18 months now, and we've procured about 80% of the equipment for this next level up plant. Here's a view of the next one beyond that, which is going to be 10 times level 1 to level 2. And the point is existing infrastructure is a huge part of the story. Right next to our land, we share a fence line with a 10 million ton a year bulk handling facility that can unload and offload huge ships. And they're down to a fraction of their original capacity. So we'll have access to this existing infrastructure, which may not even be replicable, because for the many reasons you can imagine. Yet, there's places like this all over the world, at ports around the world, where there's existing infrastructure. And here's the power plant where we're moving the solution across the street to absorbers right next to the CO2 emission sites, capturing the CO2, bringing it back as carbonate. So we've done a lot. We have a subsidiary there called San Francisco Bay Aggregates, and the demand for our product is just completely overwhelming. I mean, it's not 10 times, it's not 100 times, it's way more than that. And so, we're trying to think about ways to expand faster, and a lot of people are offering their services to help us do that. But we're being pretty careful, getting into concrete projects, that we think are going to really show the potential of making the built environment carbon negative and the principal sink for the CO2. And we're focusing primarily on ports. Ports have great transportation. They have CO2 emission sites. They have a lot of the things you need to really build a significant hub. And that's sort of the, sometimes you say, are there any grownups in the room? When people are talking about these fantastical, huge projects with pipelines and government subsidies and all that, it's sort of hard to envision how they're going to happen. But we're trying to be more realistic and say, okay, if we go to South Korea, Incheon Harbor has the following logistical aspects, and here are the people that'll buy the concrete, here are the people that have the CO2, and piece together projects that are more realistic. But here's what a project looks like. So in here, what you see is these red lines are solid materials, like old concrete or new product. The blue is a bicarbonate solution, which is what we make in the first fraction of a second when we absorb the CO2. And the gas is the flue gas, which can vary from very dilute to very concentrated. So from a central Blue Planet location, like the one I just showed you in Pittsburgh, we can send out a capture solution like across the street to the Calpine plant, like we're doing in Pittsburgh. Capture the CO2, bring it back. Capture the CO2, bring it back. Or we can be co-located right next to a power plant and just take the flue gas in ourselves and do the absorption right in place. And then outgoing finished goods, limestone aggregate, incoming waste materials for calcium. Here's what that looks like in reality. This is a site we're working on near Paris. And the yellows are where the gas is coming from. the CO2 source, and a whole bouquet of different CO2 emitters. And they're not always emitting at the same time or the same stuff, same concentration. And the blue lines are the same blue lines in the previous diagram, where the bicarbonate solution is going out and picking up the carbon and coming back to make more finished goods that are going out on water. You're always on water. So that's how we're looking at it. And we're growing as a company based in Los Gatos. We've got some amazing people affiliated with us, from the head of the Stanford Carbon Storage Institute, managing director of the Carbon Removal Institute at Stanford, to some of the great mineralogists and engineers. This guy was chief scientist for Shell for 30 years. They're closely associated with the company. On the built environment side, same sort of thing. Early members of the Green Building Councils, famous architects, the guy that invented Earth Day. And then similarly, we have a government affairs area. This guy, for example, wrote the Montreal Protocol. He was the main author. It's thoroughly lived climate pollutants protocol. This guy was head of the GSA, which is all the buildings owned by the US government. He's the reason they have to be LEED certified. So we've got quite a bit of people on that front. But I'm going to stop because I don't know how far I've gone, but I think that's a good time to stop.
That's great. You're well within time. We have certainly time for questions. So we have a number of questions, I think, in the chat. Mostly procedural, but we'll get to those in a minute. If anyone would like to ask a question, please raise your hand, preferably using the reactions icon at the bottom of your screen. And I see Suds Jain has his hand up already, so we'll let Suds ask his question. Go ahead.
Thank you, Brent. I visited Blue Planet with Armand Nukermans a while ago. So it's very impressive what you guys are doing. Interesting, your shift to the aggregates. I guess my question is that, calcium carbonate is not very hard, has a hardness of 3, whereas like granite has a hardness of 6 or 7. So does that limit the applications where the concrete can be used?
Well, yeah, 71% of the aggregate in concrete, according to the textbook, is limestone already. But yeah, you're right. The different carbonate minerals all have hardnesses around 3, so they're much softer, which is why they're used for sculpture and things like that. But there's a small market for high strength concrete, which would be, 10,000 PSI. Most concretes are, typical sidewalk would be 3,000 PSI to, construction. I'm talking compressive strength might be 5,000 to 7,000 PSI. And there is an approach where you use a granite aggregate to achieve that really high compressive strength. But in terms of the majority of concrete, you're not trying to achieve 10,000 PSI. There's one interesting twist on it. There's a company out of British Columbia that's doing aggregate pebbles. And they're claiming, and they're doing this, that they can use less cement and use more aggregate, but it's the stronger, granite. And therefore, by using less cement, you lower the carbon footprint of the concrete. So that's a pretty interesting approach.
Okay, but you're saying like the majority of uses like sidewalks can be fine with limestone.
Yeah, or structural applications too. I don't know what the number is, but probably 5% of all concrete or less is specified for more than 10,000 PSI. It, my bone cements that I used to do orthopedic surgery, and I have bone cements at every operating room in the world that does orthopedic surgery. We'd get up, 5,000 PSI to 10,000 PSI cements, and those are really strong cements. But yeah, 80% of the market is sort of 5,000 PSI. That's a big generalization, though.
Thank you.
I will say one thing, though. Limestone has a much higher albedo than almost any other rock that we know of. And something that's big for architects these days is the albedo, when they're doing the heat calculations on the south-facing walls. And Lawrence Berkeley Labs got a $250,000 grant to take Blue Planet's aggregate and characterize it using solar reflectometry, which we do too. And now all the roofing companies are looking at these granules, because we can also make them colored and still retain the high reflectivity. Yeah, I've seen Armin every now and then. He's working on seeding clouds these days.
Brent, we've got a couple questions in the chat. And let's see, one of them is, let me see if I can find it. From Barry Burr. On a planetary scale, will the oxygen removed from the atmosphere cause new problems? 2 or 3 times oxygen for each carbon sequestered.
Well, we could do the math on that. Does anyone know in regular atmosphere what percent is oxygen? It's just a few percent, right? But it's way more than
oxygen's 20% and carbon dioxide is 0.04%.
Yeah, so it would be pretty hard,
right,
for that to be a problem. Yeah.
And I see a couple of hands raised. One from Adam.
Okay, Adam's hand is up. Gary, we may have dropped off.
Oh no, Gary's got his hand.
I'm still here.
Okay, Gary, you were up first, though.
Oh, okay. Well, it's sort of continuation of what Suz was saying. So I gather your process you feel is applicable to most applications where concrete is needed, but maybe not the high strength one. Is that?
Let me say that a little differently. We haven't put any effort into making a ultra high density, material, and compressive strength of a linearly elastic brittle ceramic material is inversely proportional to its porosity. So we do have some advanced projects where we're doing that, but there's really no need for it in the market. And in fact, it's negative because it makes the concrete heavier.
Okay. And then I guess you're, from the way you phrase things and not needing the subsidies, that you will be cost competitive to current techniques of mining and crushing aggregate.
Yeah, and actually, one of the debates is, should we charge a premium? On one hand, you should say, of course not, especially if you're focused on government procurement. But, we see what we're doing primarily as sequestering carbon dioxide. And if I inject it down a hole, the government will pay me, 45Q subsidy for doing that, which is a lot more than, a yard of rock. But we're actually doing a better job sequestering the CO2 than what the government's paying people to do, or the oil companies. And so there's been a lot of work on that by our built environment board, trying to understand how owners and specifiers look at it. The calculations consistently show that, for example, if a yard of concrete in the Bay Area is, say, $200, if you charge $300 to recognize the value of the sequestering of the carbon, it would be reflected in the per square foot price of the building as less than 0.5% increase in the way the owner sees the building, which is on a per square foot basis. And that's sort of how it works when people are looking at their options to have a carbon neutral building. They just want to know if it's going to cost them more. And so the point is, if you said to anyone who's owned by Microsoft, would you pay a 0.5% premium to be carbon neutral versus the other options available to them? There's, it's absolutely.
Okay.
Okay, thank you. Adam.
You.
Oh, great. Well, thank you, Brent. I think this is a great place to dump a lot of captured CO2. It's clearly better than dumping it down holes. But my question was, one of there are lots of big knocks on CCS, but one of them that mostly comes out of Mark Jacobson over at Stanford is about the power used in doing it. Like if you were going to power it with clean energy, you'd be better off just like displacing some coal power somewhere else than you would in the whole process of capturing the carbon. You mentioned your power numbers are a lot lower. Like maybe it's just a bit of a softball question, but how does what you're doing fit into that argument?
Yeah, no, that's a great idea. There are a lot of stuff coming out that is dependent on renewable electrons. This whole direct air capture field, they're planning to take electrons off the grid to capture CO2. But if you do the math, their LCA or life cycle carbon analysis, shows you'd be better off not doing it at all, over and over again. There are exceptions like Climeworks up in Iceland are running the capture equipment off of geothermal energy in Iceland. And that's how they sort of make it work. And then they inject it into basalt to sequester it. But that's what the government's subsidizing right now is, the use there. It's how you draw the box, and if your box is the whole world, some things make a lot of sense, or if you narrow the box, and it's like gerrymandering, if you will, they can set it up so that it, the math adds up, but it really doesn't add up. Our process, we call that a parasitic load. So, if we're capturing CO2 from 100 megawatts of power, we use about 9 megawatts of power to do what we're doing. So it's roughly a 10% parasitic load to accomplish what we're accomplishing, because we pump water around, we move rock around. So it's not like we don't have some sort of parasitic load, but the parasitic load of most direct air captures, if they weren't dependent on renewable energy, which we could say too, but we think that's cheating, it would be like 400%.
I have a question, if I may. Is there a preferred aggregate that you use? And is there any shortage of aggregate? I mean, is that ever going to be a limit when when we've built enough and we're not knocking it down so much anymore?
Yeah, so there's a global shortage of aggregate right now, and the reasons are involved with, at least in the northern hemisphere, permitting. There are some places that have plenty of aggregate, like Edmonton, or but there are places like Florida, California, Japan, Taiwan, the Middle East, most of Europe, parts of South America, where they have to bring in aggregate from very long distances. And it's not the cost of digging out of the ground and sorting it and washing it. It's the cost of moving it and the carbon footprint associated with it. It's really all about transportation, when it comes down to the economics. And that's the important part about, any carbon management system, is how long is it going to take to build it? How much is it going to cost? And how energy intensive is it going to be to operate it and maintain it at these large scales sustainably? And if we can't get it done by 2040, it's going to be tough. We need to start asking the very first question: could we do this by 2030? You know, and if we can't substantially get it out there in the next 7 or 8 years, you know, we better start thinking more about adaptation.
Sud, do you have another question?
Yes, I do. Thank you, Brent. So you're getting your calcium from old concrete, it seems.
In San Francisco, yeah.
If we're building more and more stuff, you're going to run out of old concrete, I guess. And so where else do you get your calcium?
Well, yeah, I mean, whether you're going to run out of old concrete or not, it depends on the location and the market and a lot of things. You know, I just noticed someone had told me this, but at SFO, they built a seawall around the runway because of sea level change. And the fact is about, I won't give a number, but a significant amount of the buildings on Earth are made out of concrete. And the majority of them are at sea level. And concrete just doesn't do well in salt water. You know, it's like that apartment building in Florida, stuff like that. So most of the people speculating about the availability of waste concrete are looking at the effects of sea level rise on concrete, because you're going to have to tear down about half the buildings in the world and move them to higher ground. And it's going to take an enormous amount of material. Instead of mining new rock, if you could plow down the existing buildings and grind them up and reuse them, you know, that might be one of the plausible pathways. But yeah, I quickly showed one of the other slides of all the different, we call it geomass, and it's a word we made up to copy from biomass. And it just means geologic materials that have calcium, magnesium, alkalinity, that kind of stuff. You know, and we're working on a plant up in the Great Lakes region, and the geomass there is not concrete, it's steel slag, which has a very high percentage of the stuff we're looking for. We've recently been using a very common type of rock called basalt, and it gives us, you know, what we need. But we have a whole scientific group that just works around the geomasses. We currently have a CRADA with the National Renewable Energy Lab, and we're evaluating mine tailings for that use. So yeah, I mean, good question. And yeah, we have a whole bouquet of other, you know, calcium is one of the more common elements on the planet, and there's a lot of different ways to get to that. We even have one project where we're looking at produced water, which is this extra water in an oil field. You know, most of what's pumped up is not oil, it's ancient seawater, which is concentrated to a brine, which has a lot of minerals in it.
So along these lines, I know Roman concrete, I think they call it porcelainic concrete, is seawater resistant. Does your process work with that chemistry of concrete?
Yeah, I'm not an expert, although I'm going to help the faculty on a really interesting course in Italy next summer, where the students have to make concrete from available materials that were available to the ancient Romans. That's their whole project. But I might be wrong, but my understanding was that it was principally that they didn't use rebar. Because concrete doesn't fail, right? It's the rebar that fails. And there's interesting projects where they're using you know, some tough high modulus materials like bamboo, you know, which is very stable at a high pH. There have been calculations that to build the Tower of Babel at the time they built it, the only material they could have used for the rebar would have been probably a bamboo of some kind. And it's not an uncommon practice in Asia to use bamboo. But if you look at the Giza pyramid, it's I think it's about 5,000 years old. There's been a lot of work on it, and there's no rebar in the whole structure. It's all a compressive strength situation, so you don't really need any rebar. And in fact, in Giza, it was determined that all those big blocks are not blocks carved with Bronze Age tools. They're actually poured concrete, but the aggregate is a limestone. It's a common nummulitic limestone that's common in the Nile region. And they were literally pouring, we think, building forms and pouring the concrete.
Oh. Okay, I don't see any hands. Anna, your hand was up for a moment, but it's back down. Do you have a question?
No, I'm withdrawing my question. Thanks.
Okay. So, oh, Adam has another question. Go ahead, Adam. You're muted.
Sorry about that. I was curious about kind of the carbon accounting side of this, like who gets to claim it? Like you guys are clearly claiming it on the concrete side, but like your power plant, what does it claim in terms of carbon emissions? Like, I mean, it feels like something needs to balance,
Right.
But I can't quite tell how this works out.
What you're trying to avoid is what's called additionality. And what that means is you're taking a credit twice.
Yeah.
And so, for example, with our power plant, they're simply going to be buying fewer allowances. So to operate in California, they're given a certain number of allowances. And, as they reduce the allowances, it's to encourage them to pollute, put out less CO2. But it's not clear. It's a little bit of the Wild West out there, because there are organizations that have sprung up and hung their shingle out as carbon accounters. And, no two firms account for things the same way. And there's this whole market called the voluntary market. And these carbon accounters, go to people like Microsoft, and Microsoft's currently, I think they've been paying over $1,000 a ton to get a credit for CO2. And then they use a firm called Vera, which offers a service to verify the legitimacy. And there's this discussions about the quality of a credit, like when they talk about cutting trees down and, all that kind of stuff. But at the end of the day, we're in the cases where we're, signing contracts, there's a business deal there. And our product wouldn't have the carbon value to the building community if we couldn't assign the CO2 credit to the concrete itself as being carbon negative. And you're really solving a problem for an emitter. But this new law, the 45Q law, gives the credit to the owner of the carbon capture equipment. That's in the United States. But there's no simple formula. We have a deal with Calpine where we own the credit, but it's gonna, if you're an oil company and you build a pipeline and you can just pay someone $100 a ton to inject it under the ground, that person's not they're getting paid $100 a ton. So, then the oil company can claim the credit.
Okay, I
Thank
see
you.
no more questions in the chat, and I see no more hands up. So I'd like to thank Brent very much for what's really an interesting and very stimulating topic, and looks like a winner technology. Though I think one question was in the chat: are you going public, or are you public? And somebody already answered that you're still a startup, although it seemed well beyond the startup phase to me. So thank you very much. And I'll just remind everyone there'll be another meeting of this group, another talk in the series. It is about business leadership in the new economy with Herman Geer and Lisa Friedman on the second Wednesday next month. I forget what the date is, but in June. So hope to see you all there, and thanks for coming, and thanks again, Brent. I will stop the
Thank
recording.
you very much, Brett.
Thanks, guys. So thanks for
Thank
staying
you.
awake.
Yep.
We'll see ya.